Example 4.7 is a common peripheral velocity example. It says that pulley A and B are connected by a belt. This is the belt that we are referring to. Pulley B and C are located along the same shaft. This is the shaft that actually connects B and C. If pulley A rotates from rest to an angular velocity of 160 radians per second in 3 seconds, determine the following kinematics quantities: angular acceleration of pulley A, angular velocity and acceleration of pulley B, angular velocity of pulley C, and finally, velocity of a point on the rim of pulley C. Let's take a look at pulley A and B. Pulley A and B are connected by a belt. And as pulley A rotates with an angular velocity omega A, pulley B will rotate as well. Now, ask yourself, this point or any point along this belt, do you think that they will move in the same linear velocity? If the answer is yes, we will know that the linear velocity along the peripheral of pulley A will be equal to the linear velocity for pulley B. Let us write this down. So the first relationship, VA, is equals to VB. Now what about omega, or rather angular velocity relationship between pulley A and B? Now we know that V is equals to R omega, and we have just established that VA equals to VB. Let's substitute and equate them. We will have RA omega A must be equals to RB omega B. And again, rearranging this equation, we will establish the relationship between omega A and omega B as shown. Now, let's take a look at pulley B and C. Again, obviously pulley B and C will rotate at its respective angular velocity. And we know that they are connected by a common shaft. And because of this relationship, we will know that omega B must be equals to omega C. What about the linear velocity of pulley B and C? Same approach. We know that V is equals to R omega, and since omega B is equals to omega C, all we need to do is to substitute the values into it and establish the relationship as what we have shown previously. VB will be equals to RB over RC times VC. Let us move on to solve example 4.7. But before we start, let us pen down what we know. We know that these are the equations for linear and angular bodies. And we have just established the angular and linear velocity relationship between pulleys A, B, and C. So part A, we are asked to find the angular acceleration of pulley A, which is alpha A. Now, a simple application of the angular acceleration formula and substituting the values that are given in this example. Omega A is 160 radians per second with a time TA of 3 seconds. Substituting in the values, we will find alpha A. Now for part B, we are asked to find the angular velocity and acceleration of pulley B, omega B and alpha B. Let's take a look at omega B first. Now we know that VA is equals to RA times omega A, which we can plug in values given in the problems, and we can establish that VA is equals to 12 meter per second. And the relationship between VA and VB, we know that they are equal simply because they are connected by a belt. So VA is equals to VB, and therefore we know that VB is 12 meter per second. Now, using the V equals to R omega relationship, we can easily find omega B equals to VB over RB, and we have 96 radians per second. Next, we'll look into how to find alpha B. So we know that A equals to R alpha, and alpha B will be equals to the linear acceleration of B over the radius of pulley B. So how do we find the linear acceleration of pulley B? Well, we know that velocity of A, linear velocity of A is equals to linear velocity of B. That implies that linear acceleration of A will be equal to linear acceleration of B. So, linear acceleration of A can be found by using RA times alpha A. And RA is the radius of pulley A multiplied by alpha A, which we have found in part A. We will get 4 meter per second square. And that implies that linear acceleration of B is equals to 4. So substituting into the formula again, we will be able to acquire alpha B, which is equals to 32 radians per second square. Now for part C, we are asked to find the angular velocity of pulley C, which is omega C. Now again, pulley B and C are connected by the same shaft. So that implies that omega B and C shares the same angular velocity. And since we have found omega B in part B, we can conclude that omega C is equals to 96 radians per second. So finally, we are asked to find the velocity of a point on the rim of pulley C, which is essentially the linear velocity Vc. And by applying V equals to R omega formula, we are able to determine Vc, which is equals to 4.8 meters per second.